Hi guys, what's the crack? So in this video we're going to go over magnetic fields, an introduction to the topic. We're going to look at permanent magnets with fixed magnetic fields, how we create magnetic fields when we have current flowing through a wire, and then a reminder of what the motor effect is. And also we're going to look at an experiment. Okay, so the first thing you know about magnetic fields is we know magnetic field lines, they show us the direction of a force, and they show us the direction of a force that a north pole will go. So how I remember it, let's say we've got our permanent magnet from when we were in younger school. So maybe our permanent magnet is made out of steel, right? Because steel is something that's always got a permanent magnetic field lines. Santa Claus lives in the North Pole, so he has to go out of the North Pole, and he has to go around the world to deliver the presents. Out of the North Pole and around the world to deliver the presents. So we can clearly see that magnetic field lines go into the South Pole and out of the North Pole, okay? We learnt also in younger schools that there's only 4 magnetic materials. There's steel, and then you have your induced magnets. And our induced magnets are always going to be iron, cobalt, nickel, and steel, okay? So there's only ones that could become magnetic. So what induced again means, it means they become magnetic in the presence of a magnetic field. So for example, if I had a bag of iron nails, let's say you're doing some woodwork, all the iron nails, if I shake the bag, they're loose, right? They're not sticking to each other. However, if I was to take an iron nail and place it inside this magnetic field, what's going to happen is it's going to get attracted, right? Induced magnets are always attracted. So let's say that's my iron nail, it's going to get attracted here. And because it always gets attracted, what happens then is that's going to become a south pole and that's become a north pole. Because we know the opposites attract. Okay, if I take my iron nail and I put it towards this side, again, it's going to get attracted. Okay, so if that's a south, this is going to temporarily become a north, and that's going to become a south. So again, iron nails are not magnetic by themselves, but we place them inside another magnetic field, they become magnetic. They become induced magnets, and they are always attracted. Other things you've learned from your GCSEs is we learned that anytime there's current flowing through a wire, we know there's a magnetic field created. Okay, and you use your right hand for this. So when you use your right hand, your thumb points in the direction of the current and your fingers curl in the direction of the magnetic field lines. So my fingers are curling towards my face. So that shows me the direction of the magnetic field lines around this wire. Okay, so again, use the right hand with your thumb showing you the direction of the current and then your fingers showing you the direction that the magnetic field lines are curling. Okay. Other things we know then is we know about electromagnets. So we know electromagnets is any time that we have electricity to make a magnet. So again, what I have here is my cell. The longer side is always the positive, the shorter side is the negative. And we know that we always draw on conventional current. And conventional current goes out of positive and around towards negative. So that's the direction of my conventional current. And what I did was instead of having a straight wire, we wrap it in a coil. And you wrap it in a coil, it's called a solenoid. And the reason we do that is you can get more wire in a cramped space, more wire in a small space, you get a stronger magnetic field. And the solenoid, the magnetic field around it, is always very similar to the bar magnet. And the north pole will always be going in the anti-clockwise direction, and the south pole will always go in the clockwise direction. Okay? So that's how we know it's going to be a north pole or a south pole. So here, if we look at it, if we follow our current flow, what's happening is we have it going up the back and down the front. So if it's going up the back and down the front, if you just imagine that again, so up the back, down the front, up the back, down the front, that's my clockwise direction. So this would be my north pole and that would be my south pole. Okay? So the magnetic field lines will come out the north pole, around the world, and into my south pole. Okay? Remember, your north pole, sorry, so the wrong way around. Your north pole is going to be your anti-clockwise direction. So again, if it was going up the back and down the front, sorry, so if I turn around, and it was going up the back and down the front, up the back and down the front, that is my anti-clockwise direction. I just was turned the other way. But yeah, so we're imagining again, it's going up the back and down the front. So up the back, down the front, up the back, down the front, up the back, down the front. That's my anti-clockwise direction, so that's why it's the north pole. Okay, next thing we did then was we looked at the motor effect. So the motor effect was when we have a loop of wire between your magnetic field, okay? And we know what's happened in the motor effect is that we can get this coil of wire to spin, okay? Because we use Fleming's left-hand rule, F equals BIL, and we're going to use our left hand now. So if I was to use my left hand, what we're going to do is we know that our left hand we have our force, we have our current, and we have our magnetic field direction. Sorry, because it's FBI, so the first thing is your force, and the second thing is your magnetic field, and your next thing is your current, so FBI. So what I can do is I can use my left hand, and when we use our left hand, we're going to figure out that the force is going to go the direction of my thumb. My first finger is my magnetic field, and my second finger is my current. So here I've got magnetic field going from north to south. So my magnetic field is going from north to south. So I move my left hand to have my magnetic field going from north to south. My current finger in this part of the wire is going in that direction. So the force here is going to come up and out. So this wire is going to have a force on it pushing it up and out. And this wire, again, magnetic field is going from north to south. My current is going in that direction. It's going to have force on it pushing it down. So clearly it's going to rotate because one side has force coming up and out and the other side has force going in. So it's going to rotate. But the problem is when it rotates through half a circle or 180 degrees, what we're going to end up with now is there's my north, there's my south. But again, if we rotate this through 180 degrees, what we have now is we're going to have our loop of wire. We're going to have this side is rotated up and around, so the current's going this direction and the current's going that direction. And again, this side's rotated up and around, so what's happening now is that's my negative and that's my positive. Okay, so that's they're called your slip ring commuters. There's my negative and positive. But pardon me, because they switched round, my contacts have switched round, everything is switched round. So again, these are your slip rings. So if this happens, what we have now is that we're going to have our magnetic field from north to south, our current's going that direction, the force in this wire is going to go in, right? So what we had was the force in this wire going up and around, but now we're going to have the force on up and around, and we keep wanting this side to always go up, right? You always want this side to go up. But what's happened now, we have this side going down. So what that really is, that's a motion where it's went through half a circle and back, half a circle and back. That's not a motor effect, we need to spin the whole way. So we don't want this to happen. So what happens then is every half turn, these contacts switch. So then what happens if we do a half turn, what we're going to end up with is there's our north-south. It does a half turn, and because it does a half turn, what would happen is that be positive, negative, and that be positive. They switch to make this negative and make that positive. So what I have now is I still have current going in this direction. So similar to was before. So then this side of the wire is always going to go up and this side of the wire is always going to go down. So it keeps spinning. Okay, so again, these things here, they're called your split ring commuters. And what they do is they switch the current every 180 degrees so they can get a full spin. We can get a full motor effect that keeps spinning. That's why we use them in things like your blenders, your hair dryers, tumble dryers, anything that spins. Okay. The last thing you do about magnetic fields is do a practical. So in the practical you do, what you have is, again, let's say we have our wire. Okay, so conventional current is what goes out of positive down towards negative. We're going to put a switch in it so it doesn't overheat. And what we're going to do is we're going to place that wire between magnetic fields. There's my north and there's my south. So if I did my Fleming's left-hand rule, what we got is our magnetic field going from north to south. Our current is going that direction. So the force in that wire would be down, right? So the magnet is putting a force on the wire down. So if we put it the other way, with that being a south and that's being a north, now what's going to happen is we have our force on our wire. So there's my magnetic field, north to south, my current going towards my right, my force is up. So now what I have is I have a force on the wire that is up, right? So the magnet experiences a force on the wire that is up. So what we can do is we can put this whole thing on a scale, right? And let's say it said we put the magnet on the scale, you hit 0 on the scale to make sure it says 0. Then what we do is we close our switch and we have our current flowing through our wire. So what's going to happen now is that because there's going to be a force on the wire up, due to Newton's third law, there's going to be an equal but opposite force on the magnet down. And because the magnet then has a force on it pushing down, what's going to happen is that our number on our scale is going to increase. It's going to record that extra force. The extra records it as a mass. The extra, because it's weight, W equals mg. So we can figure out what the size of that force is then due to our magnets and due to our current flow wire. And maybe the whole reason there is a force to begin with is because we have wires that have their own magnetic field and we're placing them inside another magnetic field. And what happens then, we're getting these two magnetic field lines to cross, and that's why they're going to be experiencing a force. Some of the vectors will cancel and some of the vectors will add. So if you find the video useful, just remember you can sign up to our online courses at the myadspace.co.uk website.